chamber, and you have the benefits that you have lower cutter head wear and lower cutter wear, which is a big advantage. But semi to that, in rock mode, you want to turn the cutter head faster, because in rock mode, excavation is really achieved by how many times you can run that disc cutter over the face, creating a chip and getting advance. So we have to have a cutter head drive system that can operate both in high torque, low speed, and lower torque, higher speed. And we're going to explain a little bit how we do that. Screw conveyor designed to operate both in open and close mode. So the screw typically is sized that it can run in semi-open mode, meaning it's not completely full of material. We can then excavate higher capacity by using a larger screw. The downside to that is that a screw will wear. So we don't want to turn the screw fast because it'll show accelerated wear. And in that case, we really want to put the belt conveyor in. So we're discussing between a belt conveyor and a screw conveyor the advantages of both in either type of mode. And we want to be able to change over that mode as quickly as possible. We've made some nice advanced or nice special features of the machine, how to switch over between the conveyor mode and the screw mode, and we can certainly show you how we pick the material up. But the biggest cause of the downtime is to change the tooling, because you physically have to go out there and change the disc cutters from a disc cutter to a scraper, or from a scraper from a disc cutter. And you're going to have that in either way. So we're trying to look at different advantages to try to excavate different geologies without changing all the tools when you go from one mode to the next. Based on that, I'm going to turn the design portion over to Brad. And Brad will discuss a little bit from the engineering standpoint of our theories and thoughts of why we do one thing over the other, and give you a bit of a overview of how Robbins is designing a hybrid machine. Brad?
All right, thank you, Doug. So now that we've kind of reviewed why you would want to consider a hybrid TBM, and Doug's giving you an overview of what's involved in the different machine types, I'm going to go into a little bit more detail of the major components of the machine. Starting off with the cutter head, again, this is the first part that sees the geology, and it really dictates a lot of how the material is handled back from the machine. What we can see here is a classic hard rock head. As was mentioned earlier, you can notice it's a very closed design, so you don't see very many openings. The other thing that you'll notice is we only have buckets on the periphery, and there's only tools on one side of that. That's because it's only picking up in one direction. A big part of a hard rock head is its efficiency on excavating rock. The disc cutters go around in a circle, and then the muck falls, or using kerf cutting, falls to the bottom, and then we pick up the rock at the bottom. And then we always have a clean invert that way. So it really minimizes wear on our tools and our cutter head, and really through the entire machine. So the machine is optimized to excavate rock with minimal wear in a very quick fashion. The other thing is, because you are in rock, we're only going to be using disc cutters. When we consider that versus a ETB head, there we go. In comparison, you look at this head, a true ETB head would probably be the bottom one, which is a spoke type head. You can see that as opposed to being very closed, it's a very, very open design. This is because the muck is flowing through it. If you're going through clay geology, you really don't want anything to stick to it. You want to be able to bring that into the machine, and this is the most efficient way to do it. As we start to go into a mixed geology, we have to build in more structure, the ability to account for cutter loads, and minimize the size of the material coming in. So we go to a mixed type head, which again is about 35% open, but in comparison to the hard rock head that we just saw, it is still a very open design, uniformly throughout. Again, it's not just at the periphery, but it's uniform throughout the head. The tools you can see are on both sides. As Doug mentioned, this is because we have to change the direction of the head, and those tools are used to bring material into the head. If especially in an ETB, it requires an awful lot of torque because you're essentially a very large mixing machine, and so we have to be able to effectively account for that role of the machine as it's excavating. So we're taking these two very different style of heads and ways of handling muck and trying to come up with a hybrid machine head. It can be demonstrated here, and as mentioned, the hard rock head, if we have the features designed in, we're able to transform, change the configuration in order to only go in one direction, which is going to really help minimize the wear. But you can see that the opening ratios from this diagram change a great deal from a very open design where muck can flow throughout the entire head to really being only even to pick it up at the periphery. So we're changing the opening ratio in order to match the mode of excavation. So how are we doing this? How are we changing the head between the two different varieties? Well, the first one that was mentioned is the machine has to be able to accept a variety of tools. We need to change from a soft ground tool, which would be the knife edge bit, to more of a disc cutter as soon as we hit the harder geology. Once it's brought into the cutter head, the ETB is flowing through. We have to be able to add a muck chute or a muck scoop in order to take that muck from the bottom of the invert and lift it up so we can dump it into our muck transport system. And then as we change more, on most hard rock heads, we don't have heavy wear protection or wear indication because we're able to go out and inspect the head in an easier fashion. And we've minimized the wear on that head. As soon as we start to deal with hybrid and ETB types, really that wear protection and wear indication becomes a very, very important aspect of the cutter head design. And then the final point would be, as soon as we're starting to get into a solid face of rock, the ability for us to change cutters and tools, a difficulty that we run into is your new tools are going to be longer or larger in diameter than the worn tools. And so if we're hard up against the face, you have a very difficult time getting the new tools into place. And so we need a method to pull the head back. In a hard rock machine, that's a little bit easier for us because we're gripping against the tunnel itself in order to manipulate the head. In the soft ground machine, since we're jacking off the tunnel lining, this becomes a little bit more of a trick as most of the weight of the machine is in the forward section of the machine. So if we just try to pull it back, we're afraid we're going to come off the segments. So we have to design in some features in order to have an efficient tool change. The tools themselves, like has been mentioned, we have some disc cutters for the harder geology. There's a variety you can see down here on the lower left of soft ground tools that are pinned to help reduce wear. As we get harder, we go into knife edge bits. On the side of the openings, on the soft ground machines, we'll have scrapers. Scrapers really just change the direction and have the material flow through the head. When we go to a hard ground, we need to take that and convert it to a bucket, which is meant for scooping. Those buckets also run much closer to the tunnel face so that you can't really have both installed really at the same time. The bucket, you want to have that clean invert where the scraper is just pulling it in with the primary tools, really breaking up that face and causing mixing. You can see here a head, which are on two very similar machines, similar size. You can see how it's dressed with a variety of tool types. In this case, the one on the left is soft ground tools, and it can be changed in the same housing, same location to a hard rock head, or a head with cutters that's more able to efficiently excavate rock. Now we're going to have a short video to kind of show a cutter during excavation. And there's a couple of things that really we should look at during this video as soon as it starts playing. The first thing that I want you to pay attention to is really how severe the duty is for these tools when they're in front of the face. Again, why we want disc cutters, and then why the wear. You can see that we achieve a lot of wear on tool steel during that. The other thing is, while the machine was tracking, you can see that the cutter was moving around a lot, so there's a lot of forces going into that cutter. So how do we account for a lot of those forces for the cutter head moving? Well, one of the things that we will install into the shield to help with the efficient excavation of the rock are stabilizers. They're essentially mini grippers that we install inside the shield, and that helps the head from moving around. It's especially important in smaller machines, but it's of great benefit in larger machines. Again, as the head turns, we want that cutter to stay on the same track for efficient curve cutting. We can install similar type grippers on the other side of some articulation joints that we install on our machines, and this allows us to hold that back end of the machine as we pull the heavier forward section of the machine back. Again, this is done primarily to help with effective cutter changes and inspections. And then finally, we have a skew ring that we install on our main thrust system. What this will do is allow us to change the angle of our main thrust cylinders for roll correction. So as the machine starts to roll in a single direction, we're able to change that angle of the main thrust cylinder, and as the machine moves forward again, the roll is brought back into a correct orientation. These are all pieces that go on the main shield of the machine, but really affect the cutter head design and how we can interface with that cutter head. To, like I said, the cutter head sets how a lot of the machine is operated and designed. With that, we come to a poll question. What is your biggest challenge when operating a TBM in mixed ground? Is it maintaining advance rate, monitoring tool wear, or preventing settlement?
And while everyone's answering that, Brad, I have another question. Have you had many mixed ground projects where a hybrid machine was used?
We have a few. We have quite a few mixed ground machines. We do have a couple with hybrid machines as well. We have some examples where we've been modified on the fly, where we go to a slurry, hybrid rock slurry system, or we will see some pictures of machines where we have installed screw conveyors and belt conveyors on the same machine. It seems like even on, especially on the EPB jobs, there's a lot of ground that is very mixed. So where a hybrid machine, again, depending on the length of the tunnel, will be of benefit. Actually, and that's something, Doug, given that he has a few more years of experience than me, is more than able to answer that.
Yeah, no, it's interesting because I see the poll came back that the biggest challenge is to prevent settlement, and that's an interesting concept, because that's exactly what this type of machine is intended to do. When you've got to maintain a face pressure, you have to maintain that face pressure for settlement. And, we're working on some projects now, especially metro jobs, where we have these mixed face conditions, rock on the bottom, soil on the top, and that is a challenge. That's a challenge not only for any type of machine, but it's really a challenge, and I kind of put it out to the designers in the crowd is not to do that. To lower the tunnel, put it in the rock, or raise it and put it in the soft ground. Don't put it right in the middle. It makes a challenge for everybody.
Yeah, and that's certainly what almost all metro, or a lot of our machines at the geology that we're seeing is, it's never uniform, it's never soft ground, and then throughout the entire tunnel are all rock through the whole tunnel. It seems like an awful lot of machines are going into mixed ground geologies, which is a challenge. All right, we've had enough time to look through that. So now that we've looked at really how that head brings in material and how it deals with it, we want to look at how are we driving that head.